numerical, but mostly numericals are there. So question is like we will give you a GSHS, we will give you an open loop transfer function, and from that you have to identify what is the type of the system. So from GSHS, number of S at the denominator, that is actually the type of the system, and I have to mention what is the type of the input. So you can see this block representation. So in this block representation, this is a closed loop system, it's a negative feedback. So RS is the input. So there are mainly three types of inputs what we will be dealing with: step input, ramp input, parabolic input. Unit step is having amplitude 1, unit ramp is having slope 1, likewise. So this is the error signal, ES. So ES is actually, you can find here, ES actually is given by difference between input and the feedback signal. So whatever is ES, generally that is given by RS minus BS. Okay. So BS is nothing but the feedback signal, RS is nothing but the set input or input to the system, that is, it can be unit step, it can be unit ramp, it can be parabolic. So RS minus BS is actually ES. So whatever is the difference between input signal and feedback signal, that is called as error signal. Now this error signal is given to GS. GS is the forward path gain. Now in the first lecture we have seen what all things are there in the forward path. So forward path can be comprising the controller, then there is an actuator, then there is a plant that we want to control. So controller transfer function, actuator transfer function, plant transfer function, plant or industry, whatever. So all these transfer functions are in cascade. Okay. So all these three things, if you multiply, cascade means you can multiply their transfer functions and you will find what is GS. So GS is having three things: controller, actuator, and plant. Then there is coming the output, CS. Okay. And feedback is taken. So there is a sensor in the feedback path. So feedback path gain is given by HS. And we are finding the overall transfer function CS by RS. We know CS by RS equal to GS divided by 1 plus GS into HS. So overall transfer function is given by TS. Now from here, error analysis, you can, first line you can see ES is equal to RS minus BS. That is error, whatever error signal is there, that is nothing but difference between input and the feedback signal. Now this BS can be written as multiplication of CS and HS. So this is a very small proof that can also be asked in the exam. Okay. So this ES is equal to RS minus BS. We are actually trying to find out what is the formula of error in Laplace domain. And when we take that error into time domain, this is given by ESST, that is steady state error in time domain. And in Laplace domain, it is ES. So ESS for t tends to infinity. Okay. That is kind of the steady state error. We'll see all those things. Okay. So ES is equal to input minus feedback. Feedback is substituted by HS into CS. Then CS is equal to ES into GS. So whatever CS you are finding here, output is nothing but input. Now input is not only RS, input is RS minus BS. So this CS equal to ES into GS, there is a third line. So substitute in case of CS here, you substitute CS is equal to ES into GS. So from here, error signal is equal to RS, that is the input, minus HS, that is the feedback, into error signal multiplied by the forward path. After all these things, you just take this whole thing in the left hand side. So ES and this thing, if you take in the left hand side, will be plus. So ES take common, it becomes right hand side only RS. Then take this 1 plus GSHS thing down. So this is a very important formula. If you are having pen and paper, you can write down. That is error, ES, error in Laplace domain is given by RS divided by 1 plus GSHS. So there is a very small proof, but very important proof, can be asked in the exam. So the question you can write down, that is proof for, you can write down the question, that is proof for the error signal in case of a closed loop feedback system. Okay, so proof for error signal for a closed loop feedback system with negative feedback. That is an important question. ES is the, so proof for the error signal for a closed loop feedback system with negative feedback. So as the negative feedback is there, this is 1 plus GSHS and numerator is RS. So ES is the error, RS is the input. Now if input is unit step, then RS is 1 by S. If the input is unit ramp, then RS you have to substitute as 1 by S square. Okay. So that thing you have to remember. And GS and HS should be given to you. So ES you can calculate in the Laplace domain, provided type of the input is given, GS transfer function is given, HS feedback transfer function is given. So with all this, I will go forward. Okay, so this formula you have to remember: ES equal to RS divided by 1 plus GSHS. RS is the input. It can be ramp, it can be step, it can be parabolic. GS is the forward path gain, HS is the feedback gain. There is an example given, that is for a forward gain GS equal to 1 by S plus 2, HS equal to 2, find what is the value of ES. So we know that ES equal to RS by 1 plus GSHS, and you have substituted 1 by S plus 1. So CS by RS, first we have found CS by RS equal to 1 by S plus 3, and whenever it is unit step input, UT, for unit step input, RS equal to 1 by S. But see one thing, the formula of CS by RS is different than the formula of ES. Okay, so CS by RS is given by, as it's given above, CS by RS is given as GS by 1 plus GSHS. So 1 by S plus 3 is the closed loop transfer function with negative feedback. But ES formula is different. ES formula is RS divided by, so ES formula is RS divided by 1 plus GSHS. Don't confuse, ES is different than CS by RS. So in ES, first we have to find what is RS. So RS is the input. If it is said unit step, substitute RS as 1 by S. Then 1 plus GS into HS. So GS into HS is 2 by S plus 1. Because in the numerical, it is given that HS equal to 2 and GS equal to 1 by S plus 1. Okay, so GS into HS equal to 2 divided by S plus 1 and RS equal to 1 by S. So from here we can find ES equal to 1 by S into 1 plus 2 by S plus 1. If you just calculate it, it becomes S plus 1 divided by S into S plus 3. Okay, then do the partial fraction, you will find error is equal to 1 by 3S plus 2 by S into 3 into S plus 3. Then if you are finding ET, what is ET? ET is the inverse Laplace transform of ES. What is ET? ET is the inverse Laplace transform. So 1 by 3S inverse Laplace transform is 1 by 3 of UT, and 2 by 3 S plus 3 inverse Laplace transform 2 by 3 into e raised to minus 3t. So if error is there, error function, that will be equal to ET is equal to 1 by 3 UT plus 2 by 3 e raised to minus 3t into UT. If you take UT common and 1 by 3 outside, you will be finding that error signal ET is equal to 1 by 3, 1 plus 2 into E, 3 raised to minus 3t. Okay, so this is how we are finding the error in time domain. Okay, so for finding error, what we require is, we need what is the type of input. That is the first thing. We need what is GS and what is HS, and then the formula is RS divided by 1 plus GSHS. Substitute RS, substitute GS, substitute HS, get what is ES, then take partial fraction if required, and then take inverse Laplace transform, and you will be finding what is the equation of ET. So that is one part of it. The second part, what is saying is, what is meant by steady state error. What is meant by steady state? Okay, so whatever graph just now, whatever equation you had found out previously, just see the equation, what is there. So this was the equation, error you had found out. So ET is equal to 1 by 3 into 1 plus 2 e raised to minus 3t ut. Substitute t is equal to infinity in this equation. So what is meant by steady state error? At steady state, what is meant by steady state? You have to substitute t is equal to infinity. So if you are substituting t is equal to infinity here, this part, that is 2 e raised to minus 3t, this part becomes equal to 0, because e raised to minus infinity becomes equal to 0. So what is the value of et at t is equal to infinity? Answer is 1 by 3. So you can check here. Okay, so at t is equal to infinity, the amplitude of error will be 1 by 3. So there is a graph shown at t is equal to 0, at t is equal to 0, this e raised to minus 3t will be 1. So what is the amplitude of error at t is equal to 0? It will be 1 plus 2, that is 3 by 3, that is equal to 1. That's why this error graph starts at t is equal to 1. And as time progresses, the error reduces. And when at t is equal to infinity, the error we are finding is 1 by 3. And this 1 by 3 is here. So how much is the steady state error? Steady state error et at t is equal to infinity is equal to 1 by 3 units. So this is what we are trying to find. So Ct is equal to 1 by 3. So what is meant by steady state error? Steady state error formula is given by limit s tends to 0 s into es. Be very careful. S into es. And what is es? Es we have found as rs divided by 1 plus gshs. So if we want to find how much is the steady state error, that is error at infinite time, error at t is equal to infinity. Now there are two contradictory things because we are finding error at t is equal to infinity, but here we are working in Laplace domain. Okay, so here we are supposed to use initial value theorem, final value theorem, and all those things. So here actually we are using final value theorem. What is the value of et at t is equal to? So somebody is saying I'm not audible, okay, but this lecture will be posted to you, and there you can listen to the video because there all these things will be clear. If I again keep on repeating, then there will be shortage of time. So let me go ahead. You can catch me up in my video, and if you are having any doubt, you can have a discussion. If you are having any doubt, you can always send me questions, or you can have audio or video chatting with me, and I will explain the same thing to you in a free time. So this is a regular lecture, so let us not hamper the flow. So just see what is the ESS. ESS is in the Laplace, ESS is in the time domain. Okay, so this is a time domain error we are finding at t is equal to infinity, but that we are finding from the Laplace domain parameter. So this is something we have to understand, that left side ESST, that is a steady state error, we are finding at t is equal to infinity, but we are finding that from Laplace domain equations. So S is a Laplace domain thing. Es is also given by r divided by 1 plus gh, that is rs divided by 1 plus gshs. So from Laplace domain parameters we are trying to find out time domain error. This is what is the beauty of this steady state error equation. So ESS means ESS of t. What is given here? ESS, that is the steady state error. It is in time domain. Okay, this is equal to limit s tends to 0. Please don't mistake in these limits. Okay, so steady state error ESS of t at t is equal to infinity is limit s tends to 0 s into es. Now es I am substituting rs divided by 1 plus gshs. Now let's see how to find out for the same system whatever is given above, that is gs is 1 by s plus gs was how much, just check. Gs was equal to 1 by s plus 3. Okay, hs was equal to 2. Just check here. Sorry, gs was equal to 1 by s plus 1 and hs was equal to 3. So for this system, cs by rs, that is gs by 1 plus gsh is equal to 1 by s plus 3. And let us find out what is the steady state error from this formula. So this is saying rs. So rs is, what is the value of rs? Rs is 1 by s, and then 1 plus gshs. 1 plus gshs will be 1 plus 2 divided by s plus 1. So if you are just substituting here, it will come as s plus 1 into s plus 3. It will come as s by 3. So you do the same numerical. You do the same numerical by this formula. So rs is 1 by s. Okay, that s and this s gets cancelled, and 1 plus gshs. 1 plus gshs is 1 plus 2 divided by s plus 1. So s plus 1 goes in the numerator, and s plus 1 in the denominator. So s plus 1 plus 2, that will become s plus 3. Okay, so this will be s plus 1 divided by s plus 3, and we are going to get what is equal to 1 by 3. So this is limit t tends to infinity, et is same as limit s tends to 0 s into es. Okay, so final value at t is equal to infinity of the error is et. So finding the same thing by first principle is shown above. Finding the same thing is by ESS formula, which is below. So don't worry much about it. So steady state error in RC circuit step response. We have seen this response previously. So this is RC circuit. It is going up response. So there is the voltage across capacitor. Now here there is no steady state error. Why no steady state error? Because whatever input is given 1, and the capacitor also charges to the same amplitude 1. Because this capacitor is a very new capacitor, and there is no recombination inside the capacitor. There is no charge combination of positive negative inside the capacitor. So capacitor gets input voltage of 1 volt and it charges to 1 volt after a certain finite time. Hence there is no steady state error. But check this diagram below. Okay, check this diagram below. Suppose capacitor voltage input is 1, but capacitor charges up to this level. This level, let's say it's 0.8 volt. because 0.2 volt recombination or some charge loss is there inside the capacitor. So zero point 0.8 volt is the final capacitor output voltage and 1 volt is the input voltage to the capacitor. So how much is the steady state error in that case? It is 1 minus 0.8, that is equal to 0.2 volt. So in that case, ESS of T, ESS, SS stands for steady state, E stands for error, and as this is in time domain, we are giving the parameters by small. So E is small here, and in Laplace domain the same E is given in capital. Okay, so ESST is equal to 1 minus 0.8, that is equal to 0.2 volt. And there are mainly two parts. Initially when the error is increasing or when the output is increasing very fast, this is actually the transient region, and when the output is getting almost stable, this is called as steady state response. So for any time domain response, there are mainly two parts. One is transient response, when the input is building up. So when there is a lot of variation in the output, that is a transient part. And when it is almost trying to get steady, same value, this is called as a steady state part. So initially there is a transient part, and when it gets steady as t tends to infinity, then we are supposed to measure what is called as steady state error. So after the amplitude has got steady to 0.8 volt, then we find how much is the difference of output with the actual stable input. So actual stable input is 1 volt, output is zero point 0.8 volt stable. Okay, then difference between stable output and the given input is 1 minus zero point 0.8, that is equal to 0.2 volt, that is steady state error. Steady state error is actually very small, but it should be zero. If steady state error is zero, that is the best kind of system. So it is said that steady state error is an important parameter as it helps to find out system performance accuracy at steady state. So steady state means t is equal to infinity. These were the basic things, and now let us enter formally how to find steady state error and what is the definition of steady state error. It is given here, so I'll forward this notes to you, but initially this notes actually steady state error related analysis starts from page number 11 of this PDF, so be careful. Okay, so steady state error, what is the definition? The definition says that the response that remains after the transient response has died out. So initially there will be a lot of undulations, there will be a lot of high and low in the output, and maybe the output will be building up. It is not going to be stable at a certain value initially, but yes, after t is very big, after quite a lot of time, t tends to infinity, we will find that the output has become stable. Okay. So when the output has become stable, it is not showing any jitter, it is not changing frequently. That time we are supposed to measure if there is any difference between the given input and the output. So if the input given is 1 and output is 0.8, then steady state error is 1 minus 0.8, that is 0.2 volt. That is what we are supposed to find out. So the difference between the steady state response and input signal is called steady state error and is given by ESS of t. Okay. And what is the formula for ESS of t? As we have seen, in time domain it is t tends to infinity et. In Laplace domain it is limit s tends to 0 s into es. Who are you?
The first year students.
I am your mentor.
Yes, sir.
Okay.
Thank you.
Yes. So whenever there is a system, it is called as there is a kind of a closed loop system given by GS divided by 1 plus GSHS, and this ES, there is an error signal. Error signal is given by R is divided by 1 plus GSHS. So the same formula we have seen previously. Let us find out the main thing. There are actually three error constants that we can find out. So this is a very important question asked in the exam. That is, what are positional error constant, what is velocity error constant, and what is acceleration error constant. So you should be having very fundamental knowledge of limits, how to find it. So limit s tends to 0, gs into hs. This is actually the positional error constant, kp. kv, velocity error constant, it is limit s tends to 0, s into gs into hs. Okay. And acceleration error constant, that is ka, that is given by limit s tends to 0, s square into gs into hs. Now what are these three error constants? So first formula is given by this initial formula, steady state error is equal to ES is equal to RS by 1 plus GSHS, and this whole thing ES you can substitute here to find out what is the steady state error in time domain, ESST. So this is limit s tends to 0 S into ES. This is actually steady state error finding formula directly. This is one way. Another way is finding the steady state error by using Kp, Kv and Ka. What is that? Positional error constant, velocity error constant and acceleration error constant. So in these two ways you can find the steady state error. If the input of the system is a step input, then you can find steady state error. Direct formula is, if the input is step input, then steady state error is given by 1 by 1 plus Kp. Okay, and how to find Kp? Kp is found by this formula, that is limit s tends to 0 Gs into Hs. How to find Kv, velocity error constant? This is limit s tends to 0 S into GSHS. How to find acceleration error constant? Limit s tends to 0 S square into GSHS. So next case, if steady state error is to be found for step input, directly we can apply 1 by 1 plus Kp. What is Kp? Kp is nothing but limit s tends to 0 GSHS. So in that case, ESS of t, this one, the whole thing, you won't have to use the formula of Rs divided by 1 plus GSHS. Not necessary. If I am asking you find steady state error for any input for step input, so for step input, separately find what is limit s tends to 0 GSHS. Whatever you find, that is called as Kp. Substitute that Kp here, and that will be the steady state error with step input. Same thing, if the input is ramp input, you can check here. If the input is ramp input, then the steady state error is found directly by A divided by Kv. What is A? A is nothing but the slope of the ramp input. If the ramp input is having slope of 1, then A will be equal to 1. If it is unit ramp, if ramp input is having slope of 5, then it will be 5 divided by Kv. And how to find Kv? Kv is given by this formula, that is limit s tends to 0 S into Gs into Hs. So this is the formula, it is given here, ESS limit s tends to 0 S A by S square. A by S square is nothing but, if it is not unit ramp, if it is A into T, okay, if it is 2T, then what will be Laplace? It will be 2 by T square. If it is 5T, that means slope is equal to 5 for that ramp. It will be 5 divided by S square. So in that case, ESS will be limit s tends to 0 A divided by S plus SGSHS, and if you are substituting limit here, you will be finding formula comes here. So finally, if it is ramp input, so all these intermediate steps no need to remember. Just remember that if it is ramp input and if the ramp is having slope of A, capital A, okay, so it will be given ramp is having unit ramp, that means capital A is equal to 1. A ramp is having slope of 3, then means capital A is equal to 3. How much will be the steady state error? In that case, it will be A divided by Kv. And how to find Kv? Limit s tends to 0 S into Gs into Hs. So that formula is given above. So these three formulas you have to take. So you can take a screenshot now. That is, Kp is limit s tends to 0 GSHS. Kv is limit s tends to 0 SGSHS. Ka is limit s tends to 0 S square GSHS. Okay. Here there is no input thing coming, only whatever Gs and H is given, you just put it here, do the calculation, find what is Kp, Kv and Ka. So finding the steady state error from acceleration, velocity and positional error constants, this is much easier method than substituting Es, Gs, Hs, etc. Okay. So this is the second formula. So steady state error in time domain, ESS of t is equal to A divided by Kv, where Kv is equal to limit s tends to 0 S GSHS. Only thing you have to remember is A has to be the slope and it should be given slope of the ramp. Third case, if it is parabolic input, then RT is equal to A by 2 T square, Rs equal to A by S cube. Okay, in that case, what will be the steady state error? Steady state error will be A divided by Ka. And what is the value of Ka? How to find Ka? Is limit s tends to 0 S square into GSHS. So positional error constant, limit s tends to 0, GSHS. Velocity error constant, limit s tends to 0, SGSHS. And acceleration error constant, limit s tends to 0, S square GSHS. These are the three things. And once you find what is Ka, that is positional acceleration error constant, directly substitute A divided by Ka, where A by 2 is the amplitude of parabolic system. Okay. And GSHS is loop gain or open loop gain. We have seen it long back. So with this basics, we will be solving some numerical. Now here is coming the same old discussion, that is discussion about system type and system order. Okay. So GSHS is something from which we are supposed to find out what is called as system type. So GSHS is open loop transfer function. Here GSHS is given by 1 by S into S plus 2. So S plus 2 is nothing to do with type, but type is to do with whatever is the number of, whatever is the power of separate S. So here the power of separate S is 1. Hence GSHS, it's a type 1 system. Okay. So you are having a lot of confusion. So I have uploaded the PDF already. So that PDF you can check. So here it is, S as to 1 means GSHS is having S at the denominator. So power of S is 1. Hence it's a type 1 system. If GSHS is 1 by S plus 2, that means numerator there is no separate S, or power of S is equal to 0 at the denominator. In that case, here this is a type 0 system. So 1 by S raised to 0 into S plus 2. That you have to understand. And here GSHS 1 by S cube into S plus 2, S plus 4. So here there is a separate S. So there is not only one separate S, but there are 3 separate S. That means S cube. So this is a type 3 system. Okay. So this is how to find type, and from this given GSHS you can find what is the closed loop transfer function, that is GS divided by 1 plus GSHS, and whatever is the denominator you have to see that polynomial, and whatever is the degree of the denominator polynomial for a closed loop system, that will be the order of the system. So it is given here order, degree of S in system characteristic equation. So characteristic equation we find only in case of closed loop system transfer function. So whenever I am saying characteristic equation, means it's a closed loop system transfer function. There whatever is the highest power of S, that actually is the order of the system. Okay. So GSHS is equal to 1 by S into S plus 2. This will be a type 1 system. And if you find a closed loop transfer function from here, you'll be finding this is a order 2 system. Okay. Similarly, 1 by S plus 2, this will be a type 0 system. 1 by S cube into S plus 2, S plus 4, this will be a type 3 system. Okay. Let us find out. So this is a very important numerical. I'm giving you 1 minute to write down this numerical, that is find the steady state error for step input. So either write down this numerical or you can take a screenshot. This is a very important thing. Please take it down. So forward gain of the system is given by 200 divided by S plus 2, and there is S square into S plus 4 into S plus 5. All these things are there, and denominator is given like that, and numerator of the system there is 200 into S plus 2. So there is open loop pole, there is open loop 0. So open loop pole are at S is equal to 0, S is equal to 0, S is equal to minus 4, and S is equal to minus 5. So it's a 4 pole you can find in GS or denominator. Here 1 0 you can find at the numerator. And HS equal to 1. What is HS equal to 1 system called? HS equal to 1 means the system is called as a unity feedback system. Okay. So unity feedback system. So GSHS equal to GS. In that case, find what is the steady state error. Okay. So either you can find it by direct formula. Direct formula is ES. Okay, is equal to limit S tends to 0 S into RS. So that you have to understand. So this is I have calculated by classical method. Limit S tends to 0 S into RS divided by 1 plus GS into HS. Okay, so you can take a screenshot and you can write there below. That is here steady state error is calculated by classical method. That is ESST is equal to limit S tends to 0 S into RS divided by 1 plus GS into HS. So RS, as HS said that it is a step input, I have substituted RS as the Laplace of unit step, that is 1 by S, and this is the S of the formula, and 1 plus this is GS. So GS is given by 200 into S plus 2 divided by S square into S plus 4 into S plus 5, and HS is given as 1. So now if you are solving it, this whole denominator goes above, that is S square into S plus 4 into S plus 5, it goes above, and denominator it is the whole thing. So S square into S plus 4 into S plus 5 plus 200 into S plus 2. Now what you have to do is you have to substitute S tends to 0 here. If you are substituting S tends to 0 at the denominator will become 400. See, this first term S square into S plus 4 S plus 5, this will become 0 if you are substituting S is equal to 0. Here also, if you are substituting S is equal to 0, this first term will be 0. So this will be 200 into 2. That means denominator will be 400. But numerator, this S square is separate. That means you are substituting S is equal to 0 here. This will be 0 divided by 400. Answer is equal to 0. That means steady state error for this system, given system, which is a type 2 system, okay, and it's an order 4 system eventually if you find. So this is a type 2 system, and it will be having steady state error is equal to 0. What is meant by steady state error is equal to 0? This is an ideal system, very good system. That means whatever is the input given to the system, that is a step input, unit step input you are given. So at t tends to infinity, the output will reach to that unit step value, that is 1. Okay, so that is the significance of steady state error. Steady state error is equal to 0 means at t tends to infinity, the output of the system will be equal to 1. That means whatever is the given input, output of the system will reach to that amplitude of the given input. That is the significance of steady state error being 0. Okay. So this is one very simple numerical, but this is important numerical to understand the concept of type. There is a type 2 system because it is S square. S square means there is a very simple S. Okay, so these are actually positioned at origin. S square means there are two poles at origin. Okay, kind of a thing. And there is a 0 at -2, there is a pole at -4, there is a pole at -5. So this kind of system is this. H is equal to 1, feedback gain is equal to 1. That means whatever output is produced, the whole thing is fed back to the input of the system. So ESST, there is a time domain steady state error we are trying to find. Limit S tends to 0 because this final value theorem. S into ES. Now ES can be substituted as RS divided by 1 plus GS into HS. After that, you rationalize it, take the term above. Only because of this S square, if you're substituting S is equal to 0, then whole thing will become is equal to 0. Then the steady state error of the system of type 2 will become is equal to 0. It means that at t tends to infinity, the output reaches to the input amplitude. This is the significance. Finding static error constant, very important numerical. You can write down this example, that is for different static error constants, static error coefficients. What are the static error coefficients? That is Kp, that is position error constant, Kv, velocity error constant, Ka, acceleration error constant. So all those error constants you find for the given open loop gain, that is GSHS. So GSHS in this case is given as 200 into S plus 2 divided by S plus 4 into S plus 5. The type of the system is 0 because there is no separate S here. So there is a first line it is written, it's a type 0 system. That means there is no separate S here in GSHS. So type of the system is found in case of GSHS, that is from open loop gain. And open loop gain you have to find what is the separate S at the denominator. There is no separate S at the denominator, that means power of S is equal to 0. That's why it's a type 0 system. What is the first thing? Find all the static error coefficients, and from static error coefficients we will find what is the different steady state error that we can find. But steady state error finding is not the question in this example. They are mainly asking you to find the static error constants. Okay, so it's a type 0 system, and hence find what is Kp. So this is a very simple formula. Kp is limit S tends to 0, GS into HS. So this is limit S tends to 0. This is GS and HS. So GS HS is given as 200 S plus 2 divided by S plus 4, S plus 5. Now substitute S is equal to 0 here. By substituting S is equal to 0, so numerator is 200 into 2, denominator is 4 into 5. So numerator by denominator is 400 divided by 20. That comes to be 20. So all the steps, so these notes will be shared with you. So please practice all these numericals properly. So this is 200 into 0 plus 2 divided by 0 plus 4 into 0 plus 5, because after this step you can substitute the limit value s tends to 0 in this. So what we are finding is, for this type 0 system, positional error constant is finite. That means positional error constant value is existing as 20. 20 is not the main thing, but it is a finite value. It is not 0, it is not infinity. That you have to understand. So it's a type 0 system and we are finding Kp. So one thing is very clear, that if it is a type 0 system, Kp value will be finite. Kp value will not be 0, Kp value will not be infinite. Find Kv for type 0 system, S into Gs into Hs. Substitute limit S tends to 0. So this S is here and this is GSHS. Now substitute S is equal to 0. So only for this S here, the whole Kv value will become 0, like this. So if it is a type 0 system, then the velocity error constant will be equal to 0. So this is the understanding. This is type 0 system, positional error constant will become finite. If it is type 0 system, velocity error constant will become equal to 0. Same thing will happen in acceleration error constant. That is limit s tends to 0, a square into GSHS. Now you substitute s is equal to 0. Because of this s is equal to 0 in a square, you will be finding that the acceleration error constant for type 0 system will be also equal to 0. So what we have found is, for a type 0 system, we have found Kp is 20, Kv is 0 and Ka is 0. Now for this type 0 system, only Kp exists. Ka and Kv is equal to 0 for this type 0 system. If I tell you that we are giving a unit step input to the system, that means unit step means A is equal to 1. Okay, and we have seen that for unit step input, steady state error is given by A divided by 1 plus Kp. For unit ramp input, steady state error is A divided by Kv. For parabolic input, steady state error is A divided by Ka. Okay. Now you can directly find out steady state error for step input, that is A divided by 1 plus Kp. And A divided by 1 plus Kp is 20. We have just now calculated. So what will be the steady state error for the given GSHS and with step input? Answer is A divided by 1 plus 20. That is A divided by 21. If I say it's unit step, that means 1 by 21. If I say 2 of unit step, then it will be 2 by 21. If I say 3 of unit step, then it will be 3 by 21. That is 1 by 7. And accordingly, you have to calculate. So things are very easy, provided you give a little bit time. The same numerical, I have changed GSHS little bit. Only difference is, previously GSHS was 200, S plus 2, S plus 4, S plus 5. Here I have added a S here at the denominator. Now this S is having power of 1. That means this S is going to be a type 1 system. Okay. Now GSS is equal to 200 into S plus 2 divided by S into S plus 4 into S plus 5. Find what is Kp, what is Kv, what is Ka. Kp we are finding by the same formula. Kp is equal to S tends to 0, Gs into Hs. And limit S tends to 0, GSHS is given like this. Okay. Here, if you substitute S is equal to 0 at the denominator, numerator will be 400, denominator will be 0. So 400 divided by 0 will be infinity. A very special case, that is positional error constant for type 1 system will be infinity. Okay, again I'll repeat, Kp limit S tends to 0, GSHS, substitute GSHS and limit S tends to 0. If you substitute S is equal to 0, you will be finding denominator is going to be 0, numerator is 400, so 400 by 0 will be infinity. Kv, find in case of this type 1 system, so this is S into GSHS, so this is S into GS into Hs. So S and S gets cancelled, then substitute S tends to 0. If you are substituting S tends to 0, it will be 200 into 2 divided by 4 into 5, so it will be 20. So ESS is equal to A divided by Kv. So we know that if it is ramp input, in that case, the steady state error can be found by A divided by Kv. where A is the slope of ramp input. If I say it is unit ramp, in that case A value will be equal to 1. Okay, so in this case, if I say steady state error A by kV, A is 1, so steady state error will be 1 divided by 20, where this 20 is nothing but kV, that is the velocity error constant. Last thing, find what is Ka. What is Ka? Ka is nothing but the acceleration error constant. So this limit s tends to 0, s square GSHS. Substitute s square is equal to 0 and you will be finding that acceleration error constant becomes equal to 0. So if it is a type 0 system, previous case we had seen, if it is a type 0 system, in that case, positional error constant becomes finite, velocity error constant becomes 0, acceleration error constant becomes 0. But if it is type 1 system, these two examples, in that case, positional error constant becomes infinity, velocity error constant becomes finite, and acceleration error constant is still 0. And how to find the steady state error in case of ramp input, unit ramp input A is equal to 1. It is nothing but the slope of the ramp divided by kV. If slope of the ramp is A divided by kV, in this case kV is calculated as 20. So ESS of T will be A divided by 20, whatever is the value of A. If A is 1, the steady state error will be 1 divided by 20. Last thing, if it's a type 2 system, in this case find, so type 2 system, this is 10 into s plus 3 divided by s square into s plus 5. How do I know this is a type 2 system? Because here it is s square. Okay, so I told you that always check GSHS and check what is the separate s there. Okay, so it's a separate s. So this s plus 5, s plus 3, 10, they are not playing any role in system type. Okay, so this is GSHS, that is closed open loop transfer function. But whatever is the separate S, whatever is the power of that, that is going to be the type of the system. So it is S square, that means it's a type 2 system. Find what is positional error constant. So positional error constant is S tends to 0, GSHS formula doesn't change. So limit S tends to 0, 10 into S plus 3, S square, S plus 5. So here if you put S is equal to 0, you are going to get Kp is equal to infinity for type 2 system. Same thing, Kv, limit S tends to 0, S GSHS, in that case limit S tends to 0. Here this is S into GSHS. So that S and S square, so this S square is reduced to S raised to 1 because there is a S here. So this S is actually cancelling one S at the denominator. So it is becoming 10 into S plus 3 divided by S into S plus 5 because GSHS is multiplied with S. In that case, if you substitute S is equal to 0 at the denominator, then Kv will become infinite. Finally, what is Ka? S square into GSHS. Now S square, GSHS is given by 10 by S plus 3, S plus 5 into S square. So this S square and denominator S square, they cancels each other. So limit S tends to 0, 10 into S plus 3, S plus 5. In that case, substitute S is equal to 0. So it will be 30 divided by 5. Answer is 6. So one very big conclusion we can find from here is the Kp will be finite if it is a type 0 system, Kv will be finite if it is a type 1 system, and Ka will be finite if it is type 2 system. I'll repeat, Kp will be finite if it is type 0 system, Kv will be finite, finite means some value, 2, 5, 10, 20. Okay. Kv will be finite if it is type 1 system and Ka will be finite if it is type 2 system. Then finally, you can find out what is ESS, that is A divided by Ka. K is nothing but, A by 2 is nothing but the amplitude of parabolic function input. So as we have found out that Ka is equal to 6, then steady state error will be equal to A divided by 6. So for type 2 system, only Ka exists. For type 1 system, only Kv exists. For type 0 system, only Kp exists. And Kp is equal to Kv is equal to infinity for type 2 system. This is a very important table. Okay, so for type 0 system, Kp is existing. Steady state error is A divided by Kp. For type 1 system, Kp is infinity. Kp is infinity for type 2 system as well. So if you are substituting here A divided by Kv, so A divided by Kv is A divided by infinity, that is 0. A divided by Ka, that is steady state error. A divided by infinity, that is 0. Same thing, type 0 system for ramp input. Here kV is going to be 0. This is infinity. kV is coming here and error is A divided by kV. So how much is A divided by kV? kV we are calculating from the given formula, that is limit s tends to 0 s into GSHS. From there kV is found to be finite for type 1 system and A divided by kV is going to be the error. If it is a type 2 system, parabolic input, for them we can find out what is the error. Ka is nothing but the acceleration error constant and A divided by Ka is nothing but the error of a type 2 system with parabolic input. So these were the fundamentals which are very important. So pole of GSHS is called as open loop poles that we have seen. Let us see one more numerical and that will be it. So this numerical also you take down, please. Okay, so 5 more minutes are there. Please take down this numerical. That is unity feedback system GS into 20 into S plus 3 divided by S plus 1 into S plus 6. Okay, unity feedback system means HS equal to 1 and GS equal to 20 into S plus 3 divided by S plus 6 into S plus 1. So GSHS equal to GS. This is one thing we can understand. Okay. RS is given by 2 by S because it is 2 into unit step. So input given is 2 into unit step, that is capital A is equal to 2. Hence RS is the Laplace of 2ut, that is equal to 2 by S. It is given unity feedback means HS equal to 1. Okay. So hence Kp is equal to limit S tends to 0 GSHS. Okay. So GSHS is nothing but GS 20 into S plus 3 S plus 1 into S plus 6. Again the same thing. Find that this is a type 0 system. Type 0 system you will be finding Kp is finite. Okay, so substitute S tends to 0, 20 into S plus 3, S plus 1, S plus 6. Substitute S is equal to 0, so this will be 20 into 3 divided by 6. That will be value as 10. And how much is the steady state error? Steady state error you can find out, that is ESS you can find out directly, that will be equal to 2 divided by 1 plus 10. That will be 2 divided by 1 plus 10, that will be 2 divided by 11. Okay, 2 divided by 11 is nothing but 12 divided by 66. Okay, you can find out by any method. So here we have found out by the easier method. So ES is equal to A divided by 1 plus Kp, that is 2 divided by 1 plus 10, 2 divided by 11, that is 0.1818. That means the error, steady state error is 18.18%. So this is by easier method, and above this is by the standard classical method. That is ES is equal to limit S tends to 0 S into RS divided by 1 plus GSHS. So as input is 2 ut, RS is 2 by S. So this is by classical method. Okay. So this is S into 2 by S, 1 plus GSHS. Okay. Then just add it, take S plus 1, S plus 6 at the top. And this S and this S gets cancelled. So it will be 2 into S plus 1, S plus 6 divided by S plus 1, S plus 6 plus 20 into S plus 3. Substitute S is equal to 0. So what you will get at the numerator is 2 into 1 into 6, that is 12. What you will get at the denominator is 1 into 6, that is 6, and 20 into 3, that is 60. So what you get at ESS is 12 divided by 66, that is 0.1818. It means that steady state error is 18.18% of the given input. So if you are giving input as 2, that means steady state error will be 18.18% of 2. So that is almost how much? So this is 2 volt, this is almost 0.36 volt. Okay, so for 2 volt input, error amplitude will be 0.3636 volt. So this is by calculation by classical method. Calculation by shortcut method, that is ESS, this is unit step input, not unit step, 2 into unit step. So output will be A divided by 1 plus Kp, that is 2 divided by, so don't make mistake, it is 2 into unit step, that's why we have to substitute 2 here, not 1. Okay, so this is 2 divided by 1 plus 10, 2 by 11. If you calculate kV, kV will be S into GSHS. So if you substitute S equal to 0, it will be 0. Ka also will be equal to 0. So we are not calculating steady state error by using kV or Ka here. We are calculating steady state error because this is unit step. Okay, so that much was understanding about error. So first we had seen what is a proof for capital ES. So first we had proof that capital ES is limit s tends to 0 RS divided by or initially. So just let us have a recap and we will stop. So initially we had proved that ES is equal to RS divided by 1 plus GSHS. So there is a small proof, it can be asked. And then we had seen what is the formula for steady state error. So formula for steady state error is given by the final value theorem, that is limit s tends to 0 s into es, where es is rs divided by 1 plus gshs. That is classical method. Then there is shortcut method, that is find the error constants. So what are the error constants? Kv, Ka and Kp. Then if you are finding its unit step input, output is given by A divided by 1 plus Kp, that is steady state error. If it is unit ramp input, then steady state error is A divided by Kb. If it is parabolic input, then steady state error is A divided by Ka. And then we have seen what is type and what is order. So type is nothing but found from GSHS. Here SS to 1 at the denominator, that means type is 1. Here SS to 0, that means type is 0. Here S cube, that means type is 3. So from all this understanding, we can calculate the steady state error from two methods. So two numericals we have seen. One is for type 0 system, one is for type 1 system with step input and with ramp input respectively. So I'll be sharing all these notes with you. So please prepare. And in this note, the steady state error thing is there from page number 11. Be careful about that. Okay, so that's all from my side. So we have almost completed